Now we move on to the second abstract that is by Rhiannon Mellis from Great Ormond Street Hospital, London. And the title of her abstract is Prenatal Exome Sequencing for Isolated Increased Nucleotranslucency. Should we be doing it?
Good afternoon. So I'm Rhiannon Mellis, and I'm presenting this work on behalf of the PAGE Study Consortium in the UK. So the PAGE study is a large UK study that completed earlier this year, having performed targeted exome sequencing in 875 trios, where the fetus was affected by any structural abnormality, and results were reported back to couples after the end of the pregnancy. So this study and others like it have found that prenatal exome sequencing can increase diagnoses in fetuses with structural abnormalities and normal chromosomes. But the diagnostic yields vary substantially across different phenotypic groups. So we saw this in the PAGE study's interim analysis, where the overall diagnostic yield from exome sequencing was 8.5%, but actually the yield was as high as 15.4% in certain groups, such as fetuses with skeletal or multisystem disorders, whereas the lowest yield was seen where the indication was isolated increased nucleotranslucency at just 3.2%. So this raises the question of whether it's actually worthwhile to offer exome sequencing for that as an indication. Now, rapid fetal exome sequencing is soon about to be implemented in clinical practice in the UK's National Health Service. So now it's more important than ever that the clinicians who will be offering this test have a really good evidence-based understanding of which pregnancies are most likely to benefit from exome sequencing, so that they can offer testing appropriately and so that we can all counsel our patients correctly about what the likelihood of getting a diagnosis from the test really is. So now that the PAGE study is complete, we set out to do a detailed review of all of the pregnancies in our data set that presented with increased nucleotranslucency. We were aiming to look at what happened in these pregnancies, where the diagnostic variants were found, and to consider the implications for clinical practice guidelines. So first of all, we extracted from the PAGE database all pregnancies that presented at less than 14 weeks gestation with any HPO term recorded that indicated there was an increased nucleotranslucency, and that's whether that was in isolation or in combination with other phenotypes. So then we reviewed all of the available clinical information about those pregnancies, including reports from later ultrasound scans and also pregnancy outcomes, to see what happened in the pregnancies. Then, reviewing the diagnostic variants that were found, we analysed the diagnostic yields, first of all according to whether or not there were additional structural abnormalities, and secondly according to the size of the nucleotranslucency at presentation. So overall, we had 148 cases that presented with an increased nucleotranslucency, and of these, 100 were isolated, and the other 48 had other structural abnormalities on ultrasound at the time of presentation. So in total, 83 variants from 65 of these cases were discussed at the study's clinical review panels, resulting in 24 diagnostic variants being reported. We also had another 5 variants that were designated as potentially clinically relevant, and that's because they did have some plausible association with the prenatal phenotype that had been seen, but there just wasn't enough evidence to go on to be able to say that they were definitely diagnostic. Because perhaps the prenatal phenotype was just too non-specific to really be able to say. So, as we might expect, the majority of these diagnostic variants were seen in the group that had multiple structural abnormalities at presentation, and in that group, the diagnostic yield was 27.1%. Then in the other group that had isolated increased nucleotranslucency at presentation, we actually saw overall a diagnostic yield of 11%, which you'll note is quite a bit higher than the figure of 3% that I mentioned on my first slide about the interim analysis. So now let's take a bit of a closer look at this group of pregnancies. So of 100 pregnancies that presented with isolated increased nucleotranslucency at less than 14 weeks, we found that 76 in our cohort stayed that way and didn't develop any other structural abnormalities later in the pregnancy. And in fact, the nucleotranslucencies resolved in most of these cases. But I have to point out that there were 5 pregnancies that ended very soon after the referral, so didn't have any other further scans. So we can't say for those ones what would have happened with the phenotype had the pregnancy abnormalities continued. So in this group, the diagnostic yield was very low at just 2.6%. But on the other hand, we had this smaller subgroup that presented as isolated increased nuchal translucency, but then went on to develop additional structural abnormalities on later scans in the pregnancy, and there were 20 cases in that group. And here we saw a much higher diagnostic yield of 45%. There were also 4 cases where there was no additional follow-up information available, but there were no diagnostic variants found in any of those 4 cases. So now just to take a closer look at this blue group where the phenotype did evolve later in the pregnancy. So you can see from this chart that by far the commonest type of abnormality that emerged later on in these pregnancies were cardiac abnormalities. And the commonest diagnosis to be found was Noonan syndrome or another rasopathy, accounting for 4 out of the 9 diagnoses in this group. And you can see that the other 5 diagnoses we found are listed on this slide. There was a lymphatic malformation, a congenital heart disease, and various other genetic syndromes. So now we'll go back to look at the group of pregnancies that presented with isolated increased nuchal translucencies and did not develop any other structural abnormalities. So there were only 2 diagnoses made in this group overall. The first one was Noonan syndrome with a PTPN11 variant. This was in a fetus that presented with an extremely raised nuchal translucency, measuring 9.9 millimeters at 12 weeks gestation. And this is one of the pregnancies that was terminated very soon after, based on that clinical finding of the very large nuchal and the poor prognosis that goes with that. And so we don't know whether any other structural abnormalities would have developed later on in that pregnancy, but there was a post-mortem which found a cystic hygroma. The other diagnosis made in this group was of chromosome 15 uniparental disomy, and that was in a fetus presenting with a nuchal translucency of 4.78 millimeters, but then went on to have completely unremarkable scans throughout the rest of the pregnancy, and the pregnancy resulted in a live birth of a baby that had no apparent abnormalities in the newborn examination. So you'll see in this group there were also these 2 variants of potential clinical relevance found in the genes KMT2D and KMT2A. And those were in 2 other pregnancies that also had normal scans throughout the rest of the pregnancy, and both resulted in apparently normal live births. So then finally, we went on to look at the relationship between the diagnostic yield and the size of the nuchal translucency at presentation. And you can see on this chart, the nuchal translucency measurement is on the y-axis, the number of cases on the x-axis, and the diagnostic yield percentages are next to each bar. The blue bars represent those that did have a diagnostic variant, and the green parts of the bars are the undiagnosed cases. So you can see here that broadly speaking, the diagnostic yield increased with increasing nuchal translucency measurements. And it's also worth noting that we didn't have any diagnostic variants at all where the nuchal translucency was less than 4.5 millimeters. But it is also worth remembering that almost all of the cases that had a diagnostic variant also developed structural abnormalities later on in the pregnancy, regardless of the original size of the nuchal translucency. So it could be that that factor in itself is potentially the more reliable predictor of the diagnostic yield anyway. So we can see here that the diagnostic yield in our cohort from fetal exome sequencing for truly isolated raised nuchal translucency is pretty low at just under 3%. However, fetuses with increased nuchal translucency are much more likely to have a diagnosis from exome sequencing if there are additional structural abnormalities or hydrops, and that's whether that's at initial presentation or developing later on in the pregnancy. Increasing size of the nuchal translucency also correlates with higher diagnostic yields. So a practical point to consider is that variant interpretation in the prenatal setting is particularly challenging when the phenotype is non-specific, like isolated increased nuchal translucency. So when there are additional structural abnormalities present, as well as increasing the a priori likelihood of there being an underlying monogenic disorder, it also just makes the process of variant interpretation and reporting that much easier. So this all has implications for how we go on to offer fetal exome sequencing in mainstream clinical practice. One possible strategy that I might suggest based on these data would be to say that we should not offer fetal exome sequencing for isolated increased nuchal translucencies unless maybe they're very large, say above 7.5 millimeters. and instead wait for further follow-up scanning and then offer exome sequencing if there are other additional abnormalities. So if we had applied that particular strategy in this cohort, we would have avoided 83 negative tests. But on the other hand, we would have missed one diagnosis in the case of that chromosome 15 uniparental disomy, where the nuclear translucency was just 4.78 millimeters and there were no other structural abnormalities. So it's always a balance between those things. So in conclusion, our findings here suggest that fetal exome sequencing is unlikely to have clinical utility for truly isolated increased nuclear translucencies, particularly the smaller ones. But detailed follow-up ultrasound scanning after a short interval, which is already widely recommended and practiced in many centres, is a good way to identify those pregnancies that are more likely to benefit from exome sequencing. So now that fetal exome sequencing is going to be implemented clinically, there is a definite need for clear clinical guidelines and also for ongoing research to make sure that we know how to maximise the benefits of this sort of testing. Thank you very much for listening, and also thank you to my colleagues who helped with this project and to everyone involved in the broader PAGE study.
Thank you, Rihanna. Very useful study. Questions? Please. There's a microphone up the front, if we can.
Good afternoon from the Philippines. I would like to ask, when is the most appropriate time to order for the ultrasound of this fetus?
So you mean the follow-up ultrasound after the initial nuclear translucency has been found?
So if your initial ultrasound is at 5 weeks AOG, when would be the best time to follow it up?
So I'm not sure what's the best time, but a lot of the cases in our cohort were followed up at around 16 or 17 weeks gestation, and that's when a lot of the abnormalities were detected in our particular cohort.
Yeah, so this is particular for the neural tube translucent, for the neural translucencies. But there we do the congenital anomaly scan at about 24 weeks.
Yes, so in the UK we do the anomaly scan at around 20 weeks. So the cases that we had when they had an increased nuclear translucency would generally go for an additional scan at around 16 weeks and then go on to have their normal anomaly scan at 20 weeks as well.
Thank you very much.
Congratulations on your work. It's really terrific. I just have a question about the larger nuchal translucencies. I'm just wondering, is it possible that those were truly cystic hygromas? Like how are they defined? Like what was the difference between a nuchal translucency greater than 6 or 5 millimeters and a cystic hygroma? Because we know that the cystic hygromas have a much higher incidence of associated aneuploidy.
Thanks, that's a good question. For the purposes of this particular piece of work, I didn't really differentiate between increased nuchal translucency and cystic hygroma purely because the cases came from all different hospital sites across the whole country, and sometimes the wording used on the reports can be a bit variable. Some people use the two terms interchangeably, and it's a bit difficult to definitively say whether it's one or the other. So when extracting all the cases for this project, I just included all the ones that were defined loosely as increased nuchal translucency or a cystic hygroma, and I couldn't definitively say which ones were which.
So it sounds like there's an opportunity for a more detailed study design to further explore this area. So how to balance between the detection of aneuploidy and also single gene variants.
These cases all had, we knew that they didn't have aneuploidy because they'd all had a microarray. So these are cases which we'd excluded aneuploidy.
But they had an invasive sample for the microarray and the exome sequencing to be done. I think the dilemma is, should everybody with a high NT not go for non-invasive screening and go for invasive screening? So that's actually the bigger underlying question. So thank you, Rihanna.
Thank you.
Okay, and now it's Tony Burrell from Barcelona, who's going to talk to us about it's again on exome sequencing, when single gene panel or exome sequencing should be applied in structurally abnormal fetuses. Tony, thank you.
Well, everybody in the room knows that in the live-born normal population, there is 1% of chromosomal abnormalities, 1% of submicroscopic anomalies, and 1% monogenic disorders. But in malformed fetuses, these rates are higher, about 25–30% of malformed fetuses are due to a chromosomal anomaly, up to 10% a micro deletion, microduplication, and up to 10% due to a monogenic disorder. CMA, actually the microarray analysis, can detect most of the cases of chromosomal anomalies and submicroscopic disorders, but monogenic disorders are still unrevealed. The relation between monogenic disorders and mutations or gene variants are not univocal, because there are some diseases that produce, in 99% of the cases, by a single mutation of a single gene. Some cases are produced, cystic fibrosis, are due to recurrent mutations of a single gene. Others, like tuberous sclerosis, random mutations in 2 genes, and Noonan, for example, we know that up to 20 genes can be involved. And in some cases, there is not a clinical suspicion prenatally and we don't know which gene we have to investigate. So when we don't have a clinical suspicion, we can rely on genome-wide analysis. And there are different types of genome-wide analysis. We can only study the exons of the 6,000 OMIM genes. We can study all the exons of the 23,000 genes, or we can study the whole genome. In our study, we have just restricted to the gene sequencing analysis, gene panel, and clinical exome analysis, because this is what was available to us. So the objective of our study was to assess the diagnostic yield of different next-generation sequencing studies, single gene, gene panel, or clinical exome sequencing, in fetuses with structural anomalies and normal chromosomal microarray analysis. So during a 4-year period and 4 months, from March 2015 to June 2019, NGS studies was performed on fetal DNA extracted from amniocytes or chorionic villi in 90 structurally abnormal fetuses with a normal microarray, most from our center and 9 from other centers, and they resulted in 14 liveborns, 5 intrauterine deaths, 51 TOPs, and 4 neonatal deaths. The 90 NGS studies were 5 single gene analyses when there was a clear candidate gene. We performed 30 gene panels, mainly in cases of high drops or persistent nuchal translucency or in echogenic keenness. And we did 55 clinical exomes, mainly on recurrent anomalies and multisystem anomalies. So and this is the yearly evolution. So single gene analysis, we performed some in 2016 and 2017, but not more. Gene panel, we do about 8 a year, and clinical exome analysis we perform in an increasing number. The overall diagnostic yield of the overall series is 37% of the cases. In single gene, in these 5 cases, only in 1 we found the diagnostic variant. For gene panels, the diagnostic yield was similar, 37, similar to the clinical exome that was 38%. So I've already described that these are very well selected cases. In single gene analysis, we study 5 cases in which pediatricians and in cases of TOPs, pathologists thought that it was a particular disease, but we were able only to find one diagnostic variant in a case of thanatophoric dysplasia. This is the case of severe this skeletal dysplasia in the first trimester. It turned out to be a thanatophoric dysplasia. We apply gene panels in different situations, and this is in relation with which panels we have available in our setting. Initially, we performed 13 panels for Noonan. This was initially, and the last years we expanded this panel to Hydrops, and this is a local developed in our center panel. And we had a 31% diagnostic yield, 4 cases of 13 cases. It was 2 Noonan syndrome. The most successful panel was the CATUC panel, the congenital anomalies of kidneys and urinary tract disease. And in those, we performed this panel 5 times and we got a result in 4 diagnostic variant. And all those cases were autosomal recessive, and 2 of them were renal, hepatic, pancreatic dysplasias. We also performed skeletal dysplasia panel in 4 cases where we look at the genes of the panel and we thought that probably we will detect the anomaly on that panel, and we were able only to find 1 diagnostic variant. It was a spondyloepiphyseal dysplasia, which is X-linked. We performed in 2 cases of craniosynostosis and 3 cases of tuberous sclerosis. This is 1 case of Noonan syndrome with big, this is a clear cystic hygroma. It started to be increased nuchal translucency, but this is in the 2nd trimester and is a clear cystic hygroma and subcutaneous edema. This is a case of hyperechogenic kidneys, bright hyperechogenic kidneys with some ascites also. It turned out to be a Bardet-Biedl disease. And this is the case of a spondyloepiphyseal dysplasia with short bones. Clinical exome sequencing was performed in 55 cases, and we had a diagnostic yield on 38%, so a little bit more than 1/3. Was especially successful in multi-system anomalies, and when we call multi-system means that has a renal anomaly and a heart anomaly, so clearly 2 major anomalies in 2 different systems at least. And in those group of fetuses, 30 fetuses, we found a diagnostic variant in half of them, 15 cases. There were 2 cases of Kabuki, and there is a long list of cases. Also, we offer to do clinical exome sequencing on recurrent anomalies. We did in 9 cases, and in 3 we got a diagnostic variant. And there were the 3 cases autosomal recessive disease, microcephaly with simplified guidal pattern that I will comment afterwards. For skeletal dysplasias with no clear pattern that could be detected on the panel that we had available, we performed directly clinical exome sequencing and we found 2 rare skeletal dysplasias and upset dysplasia, Desbouquois dysplasia. Also with 5 CNS complex anomalies that the group of CNS in our hospital, they thought particularly that would be keen to be a monogenic disorder. We were able to detect only 1 case, a Chart syndrome. For isolated increased nuchal translucency, we perform clinical exome sequencing in 4 cases. Actually, we don't perform, they were done in a private center, but there were pregnancies that we were studying. And in cardiac defects, we performed 2 with 0 diagnostic yield. This is the case of a fetus with apparently a lissencephaly. It was a first pregnancy at 28 weeks. 28-year woman. That lissencephaly was diagnosed in a female fetus at 28 weeks. And firstly, always we perform Wef PCR and chromosomal microarray analysis. It turned out to be normal, so neither depressing neither was ruled out. And then she decided, the couple decided to undergo a TOP. And after a TOP and that diagnosis was confirmed, or at least something similar to anencephaly, so we performed this single gene analysis, the least one, given that the fetus was a female fetus, and no variants were found. 6 months later, she became pregnant again, and anencephaly was suspected at 22 weeks, confirmed at 28. She decided to have another TOP. And at that moment, we performed after TOP, because it was already decided by the couple. We performed an NGS panel with 24 genes. We found 20 benign variants, and MLPA was also performed for 5 genes. Everything was correct. And finally, we ordered a clinical exome sequencing that found 2 likely pathogenic variants in the ASPM gene associated to microcephaly with simplified gyral pattern, which is a condition very similar to lissencephaly. Each parent was carrying one of the 2 heterogeneous mutations. And this example explains very well the difficulties of using panels that have to be very updated and included similar pathologies or pathologies that conditions that can be thought that because phenotypes are not exactly the same prenatally that postnatally. If we use targeted analysis, we need a prior knowledge, a suspicion of what would be the monogenic disorder, and some conditions may be missed, as I explained. The disadvantages of using genome-wide analysis: it is more expensive, more time-consuming, more difficult to interpret. There are many secondary or more secondary findings, and sometimes the gene coverage may be insufficient. So in our center, we opted for a trade-off between targeted and genome-wide, and we think that the clinical exome sequencing is clinically very useful. So as the conclusions of our study, NGS provide a definitive diagnosis in more than 1/3 of selected fetuses with the structural anomalies and normal CMA results. That while single gene studies appear not to be much useful, we got just 20% diagnostic yield. Gene panels can be applied in specific situations such as large echogenic kidneys, 80% yield, and persistent nuchal fall plus hydrops, not only increased nuchal translucency in the first trimester, 31% diagnostic yield. Otherwise, outside of these particular situations, and particularly in multisystem and recurrent anomalies, we have a diagnostic yields of 50 and 33%. Clinical exome sequencing appears to be the elective NGS study in our setting because it is a trade-off because targeted and genome-wide studies. Thank you very much.
Thank you, Tony. Very interesting topic and very topical. Questions from the audience? There are no questions. So, how many of your cases that you didn't find a mutation on when you did a single gene test or a limited panel, did you revert to doing a bigger panel and get a diagnosis?
Yes, some, I would say 1/3 of them. But the main problem was the financial problem. That when we decided to do just a single gene analysis was because there was no more money to do anything else.
Yeah, okay.
So
let's take money out of it.
Yeah.
Okay. Let's forget the money because this is different all over the world.
Yeah.
What do you think is the ideal scenario?
Definitely to transition to a clinical exome sequencing in all cases.
So clinical exome sequencing, or would you go to a whole exome sequencing with maybe a clinical panel to interpret it?
Yes, both. I think in the future will be the whole exome sequencing, but particularly in our setting nowadays, because economics, is a main reason everywhere. No? So we are definitely, we don't have a research lab in our center, so we have to deal only clinicians with the results. So we think that nowadays, in this precise moment, for us it's the best trade-off. I mean, it will be not the future, obviously.
Can I ask another question? So in the UK, we have somebody who's about to find the money for us to implement whole exome sequencing in the NHS very shortly, I hope. No pressure, Sandy. But what about the team? How do you think we need to work in this situation?
Yes, we have a small team with a pediatrician, a pathologist, a genetic counselor, and myself, that we are considering all the diagnosis. But for this reason, that I think that because we are dealing all with clinical diagnosis, if we were dealing with candidate gene and functional studies, I mean, this small team would be not sufficient. But at least we need this 4 or 5 person.
Do you not think you need a clinical scientist? Do you not think you need a clinical scientist
Yes.
as part of the team?
Yeah.
So we're really going multidisciplinary here.
Yeah, definitely.
So thank you, Tony. Thank you for your presentation. Thank you. So now we move on to the fourth and last abstract for this session. It will be presented by Shirley So from A-Star Singapore. Welcome. And the abstract title is Machine Learning Model Revealed that Nuchal Fold Thickness Played an Important Role in Predicting Low Birth Weight Babies.
Good afternoon, everyone. So low birth weight refers to conditions where the birth weight is less than 2,500 grams, and when birth weight is below the 10th centile, it is small for gestational age. As you can see from here, SGA babies are small and have higher mortality and lifelong morbidities. In Singapore, the current diagnosis of SGA screenings includes fetal size measurements and also Doppler ultrasound measurements on the umbilical artery blood flow. And it's done in 32nd weeks during the routinely antenatal scans. However, with these conventional ultrasound methods, 46% of SGA baby is undetected before delivery. And these undetected SGA babies were reported to have higher adverse perinatal outcome, such as perinatal death, cerebral palsy, and intracranial hemorrhage. Thus, we ask the questions, can we improve SGA predictions before delivery by using machine learning? So machine learning is a type of data analysis that uses algorithm to learn patterns in the dataset and make predictions. And it has been widely applied in various medical applications, such as detecting myocardial infarctions, predicting Alzheimer's disease, cardiovascular disease, and also forecasting falls in patients with Parkinson's disease. So we hypothesize that machine learning can enhance the prediction accuracy of SGA at birth using the second trimester biometry and maternal data. To test this hypothesis, we carry out this pilot study to investigate the performance of machine learning model in predicting SGA at birth, which is defined by the birth weight below the 10th centile. So this is a retrospective study, and the study was approved by National Healthcare Group, DSRB. In this study, we included only the women with singleton pregnancy, and any cases with chromosomal, structural, or cardiovascular abnormalities were excluded. We assessed the database from January 2014 to December 2015 and extracted the patient ID, gender of the baby, gestational age at birth, and birth weight. So with this information, we are able to compute the birth weight centile using the intergrowth 21st charts. Within this year, we identified 97 cases of birth weight below the 3rd centile, 105 cases of birth weight between 3rd and 10th centile. And for the machine learning purposes, it is best to avoid imbalanced data sets between groups, so we randomly selected 145 cases of birth weight above the 10th centile to set as a control. And this information will be used as a ground truth to the model predictions. Moving on, then with this identified patient ID, we extracted the maternal data informations and also the second trimester ultrasound scan data, which include the head circumference, estimated fetal weights, nuchal fold thickness, uterine arterial RIPI, and several other measurements. And these 16 features will be used as inputs to train the model. So in these studies, for the machine learning models, we explore 3 models, where each of them uses different algorithms to learn the data patterns and make predictions. For the random forest, it constructs multiple decision trees and combines them to get the final predictions. While for the neural network, it consists of nodes and layers, and it learns by optimizing the hyperparameter within the network. And lastly, for the support vector machine, it learns by finding the optimal hyperplane to best separate the 2 groups. So for the data extracted, we randomly split them into training dataset and testing datasets. The absolute measurements of the 16 features were used as input to the model, and to account for the effect of gestational age, we also included the gestational age during scanning into the model. And the output of the model is the ground truth, which is defined by the birth rate. So during the model training, the model will learn the patterns and optimize the hyperparameters. After the training is done, the trained model will be used to make predictions on the testing dataset, which was not used during the training phase. And the performance of the machine learning was evaluated using the sensitivity and specificity. Sensitivity is a measure of the model's ability to correctly identify those patients with disease within the disease cohort. In this case, refers to SGA babies. And for the specificity is a measure of the model ability to correctly identify those patients without disease in a normal cohort. In this case, we refer to normal birth weight baby. We also want to evaluate the performance evaluations of the clinical predictions. So the clinical prediction of normal birth weight, or SGA, was assigned to each test case by investigator blinded to machine predictions based on the RCOG Ritop guidelines. And the fetuses will be diagnosed at risk of SGA if the uterine PI is above 95th centile, or the estimated fetal weight less than 10 centile, or abdominal circumference less than 10 centile. Similarly, sensitivity and specificity were computed for clinical prediction as well. So here comes the result. Here is the performance comparison between the clinical predictions and machine learning models. As you can see from here, the sensitivity of all 3 machine learning models, the random forest, SVM, and neural network, has higher sensitivity in predicting SGA as compared to the clinical diagnosis, but suffers a lower specificity. But here we want to understand how the machines make the predictions. So from the models, we are able to infer how significant of every feature in predicting SGA by computing the importance score. The importance score measures how much does the model accuracy increase when the feature is used to perform the classifications. The higher the accuracy increases, the higher the importance score. The result shows that instead of uterine RI or uterine PI, which were deemed to be important features in predicting SGA as second trimester, nuchal fold thickness has the highest importance score and was the most important feature in predicting SGA at birth. We also investigated the effect of removing nuchal fold from the model and to see what happened to the model diagnostic ability. The model diagnostic ability is assessed by the area under the receiver operating characteristic curve, AUROC. ROC curve is a plot of the sensitivity versus the 1 minus specificity. So basically, the higher the AUROC, the better the diagnostic ability of the model. Here you can see that the model without the nuchal fold, which is indicated by the blue color bar, reduced as compared to the model with a nuchal fold. This plot suggests that nuchal fold is indeed an important feature in predicting SGA at birth. We also did a few other experiments to confirm whether the nuchal fold plays an important role in predicting SGA by using different inputs combinations into the model. For the first experiment, we have gestational age during scanning, nuchal fold, and uterine Doppler indices. And for the second experiment, we added in abdominal circumference. For the third experiment, we have nuchal fold thickness and the fetal size measurements. And for the fourth experiment, we have nuchal fold, uterine Doppler indices, and also the fetal size measurements. So the results show us that the nuchal fold has the highest importance score for all the experiments that we conducted. again showing that nuchal fold thickness is the most important feature in predicting SGA at birth. We observe a similar result for severe SGA prediction at birth, where it is defined by the birth weight less than a third centile. As we can see from here, model without the nuchal fold, which is plotted in the blue color bar, has lower AUROC, and nuchal fold always has the highest importance score in all the experiments that we have. And the statistical analysis also corroborates with the machine learning result, where you can see from here, SGA neonates has significantly lower nuchal fold thickness at second trimester. One possible reason could be due to the reduced growth rate, which result in reduced nuchal fold adipose tissue at neck area. However, there are limitations in this pilot study, since it's a retrospective study, though we standardized the measurement in the clinics, but we did not account for inter-observer and intra-observer variability. And also in this study, only second trimester ultrasound biometry was considered, but not first trimester nuchal translucency or other measurements. Maternal medical conditions such as PE, preeclampsia, or gestational diabetes, and historical risk factors were also not considered in the model. And the SGA cases in this study were not reviewed to determine if there were pathological iuga or if they were detected on 32 weeks growth scan. Lastly, the SGA incident in these populations is also not representative, since our testing data sets represent a 50% incidence of SGA instead of 10% incidence of SGA. So to conclude, machine learning actually can reveal that nuchal fold thickness at second trimester was important in predicting SGA at birth. And machine learning models would definitely may reveal new insights into mechanism of disease because it has the ability to identify patterns in the data sets. And lastly, there are a lot of areas that we can explore using machine learning by investigating. We also want to investigate the robustness of the models, how well is the model in identifying undetected SGA at third trimester, the ability of the model to identify SGA at birth who has adverse neonatal outcome, and also it would be fruitful to investigate the correlations between first trimester nuchal translucency and the SGA. Lastly, I would like to acknowledge the grant and the collaborators from NUS, and Bioinformatics Institute. Thanks.
Thank you, Shirley. We have time for one question. Question from the audience? Yes, please.
Thank you very much. Very nice presentations. I am Adrian from Indonesia. I would like to ask about the correlations between the nuchal fold and the placental insufficiency. Does your machine work on algorithm could define whether the fetal growth restrictions that will develop is due to the placental insufficiency or other? Because if we only knew this going to be happen to the wave of fetal growth restrictions without noticing this is a placental insufficiency, it's quite a bit useless for us to do some interventions to make the outcome to be better. Thank you very much.
Yes, yeah, we also interested to finding out whether the models, the SGA babies that we define in this study is an intra-IUGR babies or not. But at this stage, we haven't do that, but in the future, we definitely will look into that area. Yeah.
So I think that machine learning is the beginning, and there is a lot of knowledge that we can definitely explore with the new computational tools. But I apologize due to the interest of time. We'd like to thank Sony again. Thank you. So Lynn and I would like to thank all 4 speakers of this top abstract session for sharing with us your very exciting data and for sticking to time. Now we have to move on to a very exciting session that is the first debate at this conference, and we shall pass the time to our moderator, Bryn Levy.
So good afternoon, everybody. I think this is going to be some exciting discussion that we are going to have right now. My name is Bryn Levy from Columbia University in New York, and I am very excited to kind of moderate the debate. Just to give you an overview of the format, I'm going to start off with introduction, setting the scene. We're then going to switch to our first, I guess, combatant or contestant, I don't know which way we're going to have it, who's going to be Mark Pertal, who's going to be Paul. We're going to switch to Francesca. Thereafter, each of them will have 12 minutes. We're then going to open it up to everybody, and I hope you kind of rev up with some good questions. I want you to really challenge them. Then we will give them each 5 minutes for a rebuttal, and then I will summarize. But at the end of my introduction, we are going to do an initial poll of everyone over here. And I believe there is going to be a slide that's going to explain how you do that. I believe it's going to be through the app. And at the very end, we're going to re-poll everyone to see how well our contestants did and effectively who kind of swung and won the debate. It's important to know that each of our speakers have been asked to represent a specific side. And as a disclaimer, that may not necessarily represent their own personal opinions. So give them a little bit of leeway. They're doing their best to kind of, facilitate this academic argument. Okay, so what is a rat? What is a rare autosomal trisomy? And the best way we can understand that is really in terms of understanding cats and rats. So first you have to understand a cat, which is a common autosomal trisomy. And what I have right now is kind of just a breakdown of the chromosomal abnormalities that we see at the time of CVS and amnio, and also broken down between ultrasound anomalies and not. And what you'll see right at the top are trisomies 21, 18, and 13. Really, whether it's ultrasound anomalies or just AMA, they really are right up at the top. And these are our common ones, which you should all know. We order prenatal diagnosis for it. We do rapid analysis, either by FISH or qPCR or MLPA. We get back very quick results on this, and we act on those. So only a few non-mosaic autosomal trisomies are observed in live borns. And as I said, there's the cast of characters, Down syndrome, Edwards syndrome, Patau syndrome. We know that autosomal monosomies are lethal at the earliest stages of development. We know monosomy X can indeed survive, but when it does, it's associated with clinical features of Turner syndrome. And this means that all other survivable trisomies will have to be mosaic. It's the fact that they're mosaic that enables them to survive, but in most cases, there seems to be some type of clinical anomaly. So when we talk about mosaicism, what is the clinical impact of mosaicism? It's primarily determined by the timing of the mosaic event, when it happens during embryonic development. As you can see, if it's very, very early on, it's going to be distributed to all the germ cells, all the germ layers, and then be in multiple tissues throughout the body. But even within those tissues, the proportion and the level of mosaicism there is going to be very important. So if you have a very high percentage in brain or gonads or cardiac, you could expect to have higher clinical abnormalities. And in fact, that goes back to the question Francesca was answering when she gave her talk. We can never really rule out mosaicism 100%, because unless we sample every tissue in the body, we really will not be able to know the distribution. In terms of prenatal diagnosis, remember, we get 1 cell to 2, 4, 8, etc. And at a certain stage, we get the inner cell mass that then becomes the fetus and the extra embryonic mesoderm. Remember, CVS, we are really sampling a mixing of those. So the trophoblast, which is the quick dividing short-term villi, short-term cultures, which we look at those villi, and then on the long-term cultures where we're looking at the cells from the mesoderm. So the other thing to know is we talk about confined placental mosaicism and true fetal mosaicism, and this really depends on where you see it. So here, CPM1 is defined as when you see it in the cytotrophoblast and it is absent in the mesenchymal core. CPM2 is just the reverse of that, and CPM3 is when we see it in both of those tissues. When CPM1 is subsequently confirmed to be in the fetus, we now switch and refer to that as TFM, true fetal mosaicism type 4. Similarly, CPM2, when confirmed, is now considered to be true fetal mosaicism 5, and then CPM3 is TFM6. About 1 to 2% of CVSs show chromosomal mosaicism, but it's important to know that about 87% of these are confined to the placenta, and only about 13% of these are confirmed in the fetus. And again, this is now including even common cats. So this is a mixture of cats and rats, and the chromosome abnormality has the highest likelihood of being confirmed when we see it in both cytotrophoblast and mesenchymal core, and the likelihood of being confirmed in an amnio really actually depends on the chromosomal anomaly. So, which chromosome should we worry about? If you look at chromosome trisomy 21, it is only confirmed in about 34% of cases, and what I'm speaking about now is specifically when it's mosaic, okay? So, 34% of cases, monosomy X in about 26.3% of cases, trisomy 18 in 17%, 20 and 10, trisomy 8 in about 6.6, and then trisomy 13 in about 2.4% of cases. Trisomies 2 and 7, it's most frequently detected aneuploidies in CVS, but never confirmed at the time of amniocentesis. And again, looking at the distribution of the types of chromosome abnormalities that we see. So the relationship of rare autosomal trisomies to NIPT, this obviously is being encountered with greater frequency as we expand our whole genome surveys in the context of NIPT. And if we look at the series of over 6,000 consecutive NIPT cases, about 1/5 of the abnormal cases, excluding microdeletions, had a rare autosomal trisomy. And this comes from the Pescia study, which was done in 2016. There you see the bottom right of the abnormals, again, focusing specifically on the abnormals, 1/5 of them being a rare autosomal trisomy. Francesca showed this as well in a more expanded study. Mine wasn't as expanded as hers. It was up to 2018. And over here, if we look at these as a percent of all the abnormalities, it represents about 0.4% of the total cases that we look at. And again, if you look at the frequency of the rare aneuploidies in NIPT, it looks very similar to that what we see at the time of CVS. So that's a very quick introduction to rats and cats. I think now, there we go. Okay, so everybody should now be grabbing for your apps. There we go. So you plug the URL into your phone. It looks like you can use a telephone as well. And message if you put that number in. I'll give you all a couple of seconds to do that. And very often when I'm trying to do this, it goes to the next page. So I'll. Okay, the number is. Well, I think I can. Okay, for those in Asia, Africa, and the Middle East, you could put in +61 429 883 481. And the website, well, I don't know if I can even read that. It looks like
here's what I found.
paulev.com/ISBD 2019. What? Where's the 4? Oh, you have to vote for. Oh wow, was I easily swayed there? Okay. Okay, go next. Okay. Now we vote. Contrary to what Mark said, you can vote for or against. Is there anything I have to click? Okay. A is for, B is for against. It's changing, okay? Oh, it's regressing to it. Okay, so it looks very towards the middle with the fours having a slight advantage. It looks like it's 54 to about 46 right now. So I am going to bring up Mark and see whether he is able to push his numbers right up. And then we're going to bring Francesca out afterwards. Thank you, Green.
Okay, I'll just start off with a few disclosures. Firstly, I'm an employee of the Victorian Clinical Genetic Services, which is a not-for-profit provider of genome-wide cfDNA screening, and we derive income from that testing. Can you hear me? Yeah. Okay, I'll keep speaking loudly. VCGS has also thank you. VCGS has also collaborated with Illumina and received funding for a clinical study that assessed the performance of an automated genome-wide NIPT sequencing platform. But I have nothing else further to disclose. Okay, I'd like to start by just talking about the origin of cell-free DNA and its relationship to CVS. So this is an embryogenic model that Diana Bianchi published about 25 years ago. It basically shows the way that cells divide through that early embryo. I just want to point out that, and most of you will know this, that the cfDNA is derived from the cytotrophic blast component of that early blastocyst. Further down the bottom end, where the inner cell mass is, other placental structures are also formed, the mesodermal core of the chorionic villi, the amniotic membranes, etc. And perhaps only 3 or 4 cells in that early blastocyst would go on to form the embryo. But the bulk of the cells are derived from cytotrophoblast. You can see that it's a long way from the embryo, which is down on the bottom right there. So cfDNA screening essentially is a liquid biopsy of the placenta, the entire placenta. Quite different to CBS, which is a localized biopsy, and which is biopsying both cytotrophoblast cells and mesenchyme. Everything old is new again, so I thought I'd just pop in these two presentations from John Wolstenholme and Wendy Robinson. They're sort of seminal papers that were published in the mid-90s looking at the distribution of rare trisomies in CVS material. And what John found, the paper on the left there, was that there's a non-random distribution of rare trisomies in the placenta. So, for example, we see trisomy 3 is often confined to the cytotrophoblast. We don't see it so much in mesenchyme. Trisomy 2 is often confined to mesenchyme. We don't see it so much in cytotrophoblast. Trisomy 7 is often present in both tissues independently, but not together. And occasionally you'll see chromosome abnormalities present frequently in both tissues, like trisomy 15. Often these have a meiotic origin, and the paper on the right from Wendy Robinson is talking about when we see high levels of these trisomies in the cytotrophoblast, and sometimes extending into the mesenchyme, these fetuses are at increased risk for adverse outcomes. So there's John's little diagram there on the right. This is all rare autosomal trisomies now plotted into that diagram. I don't know whether you can see it that well, but the open circles are normal pregnancies and the dark filled in circles are abnormal pregnancies. So these adverse outcomes include things like spontaneous loss, intrauterine death, fetal growth restriction, neonatal death, and significant congenital abnormalities. But the thing that I want to point out here is that if you can't see it, the open circles run along the bottom and up the left-hand side, the y-axis there. But up the top, we have a large number of closed dark circles, and these are pregnancies that have very high levels of trisomy in the cytotrophoblast, and in the top right-hand corner, pregnancies with very high levels of abnormal cells, so rare trisomies in both cytotrophoblast and mesenchyme. And these pregnancies are at very high risk for abnormal outcomes, and it's because they're meiotic conceptions rather than mitotic errors. So with mitotic errors during development, if there's a gain of a chromosome abnormality, it will usually be present just in a specific tissue like the cytotrophoblast or the mesenchyme. This, we're going to sort of jump ahead 25 years now, look at the RAP frequency in cfDNA literature, and Francesca put up some similar data. This was, I think I put this together late last year, and at that time about 570 odd rare trisomies have been reported in about 170 pregnancies. You can see that the most common trisomies that are reported are 7, 15, 16 and 22. But as Francesca pointed out, the frequencies between these studies differ quite markedly. So if you look at the bottom there, Scott et al. Last year had a frequency of just 0.12%, whereas towards the top, Preskia had a frequency of 0.78%. So there's a sevenfold difference there. So why is that sevenfold difference present? And we'll talk about that in a moment. In my own laboratory, using the same technique over 4 years, and we've done genome-wide screening for 4 years now, we've seen the same frequency of trisomy using our technique over the 4 years. It hasn't changed. It's been about 0.34% or thereabouts. At the time that we test pregnancies using our method, we test 90% of our pregnancies between 10 and 12 weeks, and it's usually as a primary screen, not a contingent screen. I think that's all I want to say there. Oh, sorry, no, I apologise. The frequency, the highest frequency that you can see there is Diane Van Opstal's Trident study paper, where it nearly reaches 1%. And there's a reason for that, and that's because in Diana's study, that was Diana's study, that was a group of pregnancies that was based on contingent screening. So in those pregnancies, all the women have had combined first trimester screening, and then a high-risk combined first trimester screen then dictates whether they might elect NIPT. And we know that in combined first trimester screening, some of the rare trisomies, and particularly trisomy 16, have very low Pap measurements. So the median mom for a trisomy 16 pregnancy at first trimester combined screening is about 0.1 mom. So what happens in Diana's study there is her population is enriched for trisomy 16 pregnancies. And indeed, nearly 40% of all the rare trisomies in Diana's study were actually trisomy 16 pregnancies. So I just wanted to point that out as well, because that's what helps make these frequencies different. So the primary reasons are the referral population. Was it a primary screen or was it a contingent screen? That will change the frequency of rare trisomies that are seen. What was the gestation of testing? Was it 10 weeks, 13 plus weeks, 16 weeks? And the earlier it's done, the more you will see, and I'll talk about that in just a moment. The use of ultrasound prior to blood draw. You saw in the Scott cohort at 0.12%, which is quite low. That's a group in Sydney, and the bulk of their patients are actually scanned immediately prior to blood draw. So any miscarriages that were present with a rare trisomy are then filtered out of their cohort. So you see the numbers look lower. And also, obviously, the algorithms that are employed can also influence the outcomes. I was very lucky to be able to collaborate with Professor Bianchi and Illumina on this study that was published in Science Translational Medicine a couple of years ago, where we were looking at rare trisomies in about 80,000 pregnancies, about 16,000 from my own laboratory. And in my own labs group, we had the outcome data from the bulk of the pregnancies. What we also learned while we were doing that study was that you could stratify the risk of an adverse outcome by trying to calculate the mosaicism of the cell-free DNA for the rare trisomy. So when we were looking at abnormal outcomes like miscarriage, true fetal mosaicism, uniparental disomy, severe growth restriction, we found that the mosaicism calculation usually came out at 1, meaning that the cytotrophoblast component of the placenta was about 100% trisomic for that abnormal chromosome, the rare trisomy. And you can use this mosaicism estimation to help predict whether pregnancies are going to have complications. We found that in instances where that mosaicism ratio was much lower, the pregnancies generally didn't have any complications related to growth restriction or other problems. So I don't have a pointer, but the identity line that you can see there, so at say a fetal fraction at 10% and a trisomic fraction at 10%, it will meet in the middle on that diagonal line. And that will represent about 100% trisomy, because our trisomic fraction, or our effective fraction, equals the fetal fraction. If the fetal fraction's high and the trisomic fraction's low, it indicates that there's mosaicism present. Generally, we plot the counts across the chromosome to make sure it actually is a full trisomy rather than a segmental imbalance. But you can get really good information by using the data in this way. So what are we seeing in our laboratory? So this is all pretty much unpublished data at the moment. We're still running at about that 0.34%. We've got 182 pregnancies here, and I've got outcome data on 163. 75% of them were early miscarriages. Now, I want to make a point here now. Patients aren't sitting around after counselling waiting for their miscarriage to occur. What actually happens is we report these rare trisomies. The patient's advised to have a scan. And usually the pregnancy is a missed miscarriage. So at the time the patient's had the blood taken, the pregnancy's already failed. Okay, it's not like it's going to fail in 3 or 4 weeks' time. Very rarely that will happen, but it's a minority. Generally, the patient's told that they've miscarried. They're obviously grieving about that, but at least they have a cause for that miscarriage. And I would say that those 75 patients have got great clinical utility out of that test because they've had a cause of their miscarriage. If they had had a standard NIPT screen, they would have got a normal result for 13, 18, 21, and then they would have miscarried and not known. Or the test might have failed for a technical reason, because it sometimes does if a rare trisomy is being used as a denominator. So I just wanted to make that point. There are 88 continued pregnancies with known outcome. True fetal mosaicism was observed in 19% of those, so that's quite high. Uniparental disomy was observed in 18, although they're not all pathogenic UPDs, but some of them are, and I'll show you that in a moment. 23% of the pregnancies had birth weight less than the 3rd centile to the 5th centile, so they were growth restricted. There was preterm delivery observed in about 17% of pregnancies, so that's a delivery prior to 37 weeks. There were congenital abnormalities observed in 10%, and I can't see the bottoms. There was an uncomplicated outcome in 30%. Now that uncomplicated outcome is relatively low because of, actually that's excluding the miscarriages. Some of these other pregnancies will still result in babies that do quite well in the longer term, okay? But these are 30% of uncomplicated normal births, so no UPD, no true fetal mosaicism, no obvious growth restriction. That's similar to what's been reported in other studies. I know in Diane Van Opstal's Trident group, the normal pregnancy outcome, if you remove small for date births, is somewhere around 50%. Here's the miscarriage outcomes, and there's some really interesting data here. If you look at trisomy 15, we've reported 44 pregnancies with trisomy 15, and 39 of them were miscarriages. Now, they're almost all, or they are all, missed miscarriages, okay? So the patient's already lost the pregnancy. Only 5 of those pregnancies continued, and those pregnancies were healthy pregnancies at ultrasound, and they continued as healthy. But there's a twist, and we'll look at that at the moment. You can see for chromosome 14, which is another imprinted chromosome there, we've only seen 6 pregnancies, but 5 of them were miscarriages. They were miscarriages, and only 1 pregnancy continued. So out of those 2 quite significant chromosomes involved in imprinting disorders, although there is 39 and 44 and 7, over 50 of them, there's only 6 pregnancies that we're interested in. They're the ongoing pregnancies. What happened to those? You'll also see that trisomy 22 and 16 to a lesser degree have relatively high miscarriage rates. Trisomy 7, which we know is mitotic, there's no miscarriages there, and that's what we would expect for CPM. So here's some UPD outcome data. Let's look at 15 and 14 again. So we had 6 pregnancies with trisomy 14. Only one of them continued, and it has maternal UPD 14. So it's a pathogenic syndrome called Temple syndrome. Of chromosome 15, there were only 5 pregnancies that continued, and 2 of the 5 had maternal UPD 15 causing Prader-Willi syndrome. We received the placenta in another one, and it was proven as a meiotic conception that it corrected. So it was lucky that time there was bioparental inheritance. You can see the UPD frequency is high for trisomy 16. Remarkably for trisomy 4 out of 6 patients at amniocentesis have shown evidence of UPD for chromosome 4 after a trisomy, and some UPD for chromosome 2 as well. So what I want to make it, and Francesca, I agree with Francesca about this wholly, you can't compare the CVS data with the CFDNA data or vice versa. You have to look at the data independently because there's aspects of it that will be specific for what we're doing. And I think with chromosome 14 and 15 there, it's a very, very good example. So in Francesca's chromosome 15 data, so this was a paper that was published a few years ago, 1,000 mosaics, where she was looking at UPD. Only 1 in 26 pregnancies that showed any evidence of trisomy 15 had UPD. Now, whether it's in the mesenchyme or the cytotrophoblast or both, that is well below where it should be if most of those pregnancies are meiotic. So there's a difference in the data right there and then. Probably true for trisomy 14 as well, with 2 on 12 with UPD. So again, it's looking a lot lower than one would expect if those pregnancies were meiotic. Yeah, thank you. We do see significantly higher frequencies of true fetal mosaicism. As I said, Francesca's just published a data saying that the genome-wide cell-free DNA study is showing more than a 3-fold increase in true fetal mosaics. I agree the phenotype is variable, it's hard to predict, it's difficult to counsel. Wallerstein has published many hundreds of true fetal mosaics after amniocentesis with normal ultrasounds, and we can go to that data to get some advice. But he assessed that none of the pregnancies were at low risk, they were all at increased risk for something. So there's definitely some uncertainty in that, but we do need to deal with uncertainty quite frequently. At prenatal diagnosis, the trisomy 16 is the best documented one. We all know that the outcomes are very severe there, or the outcomes are more prone to being adverse. Here's another one that you can put down with trisomy 16, trisomy 2. We've seen 7 cases there. If the pregnancies continue and the mosaicism frequency is high, they're severely growth restricted, they're less than the first percentile, they'll often have preterm delivery. And we do see true fetal mosaicism. So we do advise increased ultrasound surveillance for fetal growth restriction and preterm birth. There's, for Bryn, 2 examples on the right there of true fetal mosaicism for trisomy 2 at amniocentesis in a micro. There was also some colonies with trisomy 2. The case on the right also has UPD for chromosome 2. So I'm finishing up now, so I've gone well over, and I'll thank Bryn for being good with me. But what I want to say is that rare autosomal trisomies can be used to provide more individualised care for patients. So for caregivers, we can identify pregnancies at risk for a number of adverse outcomes by directly measuring the amount of rare trisomy DNA in the cell-free DNA. And we can provide individualised care and aid pregnancy management by including things such as additional fetal surveillance in pregnancies that are more likely to be growth restricted. For patients, informed consent genetic counselling support is key. I agree with that totally. Evidence suggests that informed patients generally have a preference for wider screening, and the Dutch Trident study showed that 80% of women given a choice would choose to have all autosomes analysed. So rats are only part of the whole genome story, and the real main game is segmental aneuploidy calling, but we're not talking about that today, so I'll leave that there. Just a caveat that I'll put on, so I'm for, but I'm going to put a caveat in. Currently, the additional interpretive complexity of genome-wide cfDNA screening means that testing should be undertaken in accredited centres with expertise in genomics and prenatal cytogenetics in conjunction with adequate clinical support. And I'll leave it then. Thank you so much for allowing me to go over. Appreciate it. Put in a few against quotes.
Yeah, okay. So, first of all, my disclosures. I'm Tomalab full-time employee without ownership shares. Tomalab performs Harmony prenatal test internally, which is a targeted cell-free DNA test. I'm an advisory board member for Roche and consultant for Menarini Biomarkers. So during my talk, I will discuss about different arguments demonstrating that the benefits of screening for rats do not outweigh the harms. First of all, with genome-wide screening for rats, you don't know what you are screening for, and this violates the consolidated screening principles. In fact, this kind of test is extremely complex due to the complex nature, biological nature of the rat-positive results. This may derive from a miscarriage or a vanishing twin, or fetoplacental mosaicism involving the cytotrophoblast, and most of them are expected to be confined to the placenta as confined placental mosaicism or CPM, and not involving the fetal tissues as true fetal mosaicisms or CPM. They may be due to maternal constitutional mosaic rat or maternal somatic rat related to possible maternal malignancies. And unfortunately, there are very limited possibilities to derive the nature and origin of the rat from the sequencing data. Due to this, as this kind of test does not meet the requirement of a well-defined disorder, this kind of test violates the consolidated screening principles. The first one is that the epidemiology and the natural history of the disease under investigation should be well known. Second, rats in cell-free DNA are associated with poorly defined risks for fetal growth restriction, fetal abnormality, or pregnancy complications. In fact, most of the rat-positive results are inconsequential, 40%, or associated with a miscarriage, 27% of the cases. However, the frequency of each individual clinical outcome is extremely variable between different studies due to the variable a priori risk or a variable incidence or the variable referral indication that was, for example, in some studies was not reported or was a prior abnormal ultrasound scan or a prior increased risk after first trimester combined test, and we know that the serum component, and in particular the low PAPA, correlates with the presence of a rat in the conceptus, in particular trisomy 16 and trisomy 9. This variability also reflects the variable in gestational age at which the cell-free DNA test was performed, and the variable test cutoffs and analysis steps in the different laboratories. Genome-wide cell-free DNA test for rats is not an efficient screening for fetal anomalies and pregnancy complications. In fact, for example, a clinically significant uniparental disomy for non-imprinted chromosomes is detected every 24,000 women tested, or an abnormal fetus every 6,500 women tested. The conclusion that the evidence that genome-wide cell-free DNA test for rats is not an efficient screening for fetal anomalies and pregnancy complications is supported by other two studies. They were previous published studies. Both were retrospective cohort studies based on the comparison of the clinical outcome of CPM cases with matched controls with a normal karyotype. The first study is the study from my group that was published in August of this year. We compared 106 CPM for the clinical outcome of 106 CPM for rats with 468 matched controls for indication, maternal age and gestational age with normal karyotype on CBS, We did not include the cases with ultrasound abnormalities prior to CBS, except cases with an increased nuchal translucency or a soft marker. The results are that excluding trisomy 16, the incidence of adverse pregnancy outcomes for pregnancies carrying a CPM is not different from that in pregnancy with normal karyotype on CBS. Only CPM for trisomy 16 showed a markedly increased risk for low birth weight, spontaneous preterm delivery, and low Apgar score. The conclusion is that the only rat that maybe is worth to be investigated is trisomy 16, but the counseling in individual cases is extremely complex because the individual risks are not defined with certainty. And because most rats called out in cell-free DNA will be attributable to CPM, these data show that the cell-free DNA test for rats is of minimal benefit as a screening for pregnancy complications. The second study that shows the same conclusion is the study from your team, Mark, that was published in 2006, in which you compared the 36 CPMs with 195 matched controls with normal karyotype, and you got the same conclusions, and you concluded that these results provide the strong evidence that when a CPM is detected prenatally, the general health of the child can be expected to be comparable to adult children. There are no clearly delineated and professional society-endorsed steps for optimal patient management. A woman with a high-risk result for a rat should undergo a very extensive genetic counseling, including all the possibilities she has, including the possibility to do nothing because of the low or negligible risk or no risk for some rats to be confirmed as a true fetal mosaicism, a CVS in order to confirm the presence of the rat in the placenta, check the distribution in the different placental tissues, and determine the degree of mosaicism for possible pregnancy complications, or amniocentesis in order to exclude ATFM in the conceptus. And this data, this counseling, and CBS data cannot be used directly to counsel women with a positive cell-free DNA test result. Both CVS and amniocentesis in order to check the distribution of the abnormal cell line in both fetal and placental compartments. A chordocentesis for those rats that do not express in the amniocytes and for which the gold standard cytogenetic analysis is the cord blood sampling. A maternal karyotype, a maternal cancer workup for any fetal false positive result, including also those with a single aneuploidy and not only for those that show complex patterns. Obviously, most women perform an amniocentesis, but a normal karyotype does not necessarily exclude a low-level mosaicism in some tissues or organs, and is not informative for possible pregnancy complications. An abnormal karyotype on amniocytes is always present in a mosaic form, and this opens a big counseling issue because of the unknown genotype-phenotype correlations in relation to the degree of mosaicism and the tissue distribution due to their individual variability. And because a TFM does not necessarily mean that the fetus will be abnormal or even mildly abnormal. It could be completely normal. I remember the ACMG does not recommend offering cell-free DNA tests for conditions for which clear management options to assist patients and providers in making decisions and interpreting results are not available. There are also ethical and legal concerns. Broadening the scope of cell-free DNA testing into rats raises concerns regarding the possibility to convey a legally acceptable informed consent and fulfill the duty to inform the women about all the material limits of the test. An example of these concerns is represented by the informative leaflet for women of the Trident study. I read it very carefully and I found a lot of points of concern. First of all, it is stated that the clinical outcome associated to the unexpected additional findings range from severely abnormal to moderately abnormal, and this is only partially true because it ranges from normal or nearly normal to very severe, but the exact prediction of the clinical outcome in individual cases is not possible due to the unpredictable distribution of mosaics in crucial fetal tissues and organs. There is no mention about maternal malignancies, no mentions about other follow-up options beyond CVS and amniocentesis, no mention about the fact that CPM can be entirely inconsequential, no mention of miscarriage and vanishing twin, and no mention that follow-up testing may not provide any conclusive resolution. Essentially, another point of concern is that patients who wish to receive the best possible screening test for fetal aneuploidies, the NIPT, are required to participate in a research project and pay to be enrolled in this study. Essentially, all women who receive an expanded testing can be expected to face considerable uncertainty regarding the interpretation of the results, and these should be clearly stated before the test. Finally, genome-wide cell-free DNA-based screening for rats is essentially an opportunistic approach driven by the availability of a technically powerful technology, the MPSS. MPSS is a technology in search of a clinical need rather than a technology to solve a medical need. This technology creates unnecessary anxiety for patients that may lead to pregnancy termination without confirmation or for unknown reasons despite the normal amniocentesis or ultrasound scan. And a lot of these cases are reported in the different studies reporting the clinical outcome of rat-positive results. Essentially, in conclusion, genome-wide cell-free DNA test has intentionally and not incidentally or unexpectedly introduced the results of unclear clinical significance as the target of the screening without any evidence of its clinical utility. But despite the insufficient evidence of a clinical utility, screening for rats through cell-free DNA has been introduced in most countries, but worse than this, clinical decisions are taken based on these results. So the benefits of screening for rats through cell-free DNA do not outweigh the harms. And thank you very much. I want to thank my laboratory, the Italian multicentric, the clinical centers that participated to the Italian multicentric study of the clinical follow-up of CPM for rats, and in particular, Professor Peter Ben. Thank you.
Okay, so Francesca gets 2 bonus points already. Number 1, she was exactly on time compared to Mark. And 2, which I think is the best of all, digging up dirt on your opponent, pulling his own research to counterbalance his own argument. So that reminded me of a politician. Outstanding. Okay, so I'm going to ask, we're going to get the audience involved now, and please come up to the mics. And while you are coming up, I'm going to start off, and the first question will be to Mark. So Francesca brought her study, and then she brought your old study to show, that there really is no adverse outcomes except for trisomy 16. How would you answer that? First to Mark.
I just thought I spent 10 minutes going over time actually showing.
Okay, you got 1 minute for this one.
Yeah, some of those things. Look, I certainly think there's clinical utility there. Again, it's actually quite specific. At 0.3%, we're talking about 1 in 300 women getting these results. You take out the miscarriages, the 75 women that got a result, you're down to 1 in 600. In the UPD for the 14, 15 that I showed, out of 50-odd pregnancies, most of them miscarried, only 6 continued, 3 of them had pathogenic UPD, so we're talking 3 out of 6, so we've detected 50% at very, very, very high specificity. There was 55,000 pregnancies there, and we only said 6 of them were at risk for UPD, and we got it right 3 times. Throw out your microdeletion syndromes for Prader-Willi, do rare trisomy screening for chromosome 15, and you'll probably pick up a lot more, if that's the purpose of the test.
Francesca, I think you've made your point already. I just want to open it up to the audience. I think Yuval on the.
Thank you. They're both very convincing, and so I'll take the risk of not agreeing with Francesca on this one. I'd like to bring another point why genome-wide screening would be beneficial. Cats and rats account for about 65% of the early pregnancy loss, but even in recurrent pregnancy loss, rare autosomal trisomy account for about 50%. So Mark Pertile was convincing in that he described the occurrence of miscarriage when you find these rare autosomal trisomies, and sometimes they happen to occur. In collaboration with Tony Burrell's group in Barcelona, we studied the reverse, looking for trisomies, rare autosomal trisomies in miscarriages. Even before 10 weeks of gestation, we were able to show that using genome-wide screening for common and rare autosomal trisomies can elucidate the cause of early pregnancy loss, but even recurrent pregnancy loss in miscarriage cases, thereby allowing you to direct future workup. So that would be another argument of using it that even happens before 10 weeks of gestation. We'll show up our presentation in a couple of days on Tuesday afternoon at the genetics session.
Okay, thanks.
So can I comment? Your study is based on the detection of rats in miscarriage that are already detected that have been already assessed.
Yes.
The problem, and this is another stuff, when there is a pregnancy already ongoing without a demise already detected, the detection of a lethal condition is a very complex situation, because you cannot prevent, and this situation is not actionable. So we are assuming that detecting these cases of miscarriage is a benefit, but this benefit is not demonstrated. And I remember that the CMG does not recommend to screen for lethal conditions.
Thank you very much to both speakers. My name's Graham Sutters from Australia. Have we heard from the women involved? We've had scientific discussions by the scientists and practitioners. What do women want? And it's one thing to have a woman who is informed that she has had a miscarriage, and there's an explanation for that. And I can see some merit in Mark Berthal's argument there. But it's a very different situation to take a woman who has an ongoing pregnancy, who has the uncertainty that this rat has been identified. Has anyone published the views of women in the midst of that situation to actually tell us what they want to know? Do they find this useful information?
Thank you, Graham. I asked that question just the other day. We're doing some qualitative research with our organisation in several areas of genome-wide screening to see whether or not women actually benefit from that testing. So that will include things like translocation analysis that we do, so women who are carriers of translocations that we screen for by NIPT. It will include things like rare trisomy detection, things like that as well. So I think that's a very important question. I do know anecdotally that with the women that miscarry, and I actually do get emails from women either directly or forwarded on from counsellors. They're grieving about the loss of their pregnancy, but they're very pleased that they've actually got a cause. For those women that continue their pregnancy with a rare trisomy, again, it depends on what the rare trisomy is. So if we see something like trisomy 16 or now trisomy 2, we would put in there as well. We would say that there's a pretty well-defined clinical course for those pregnancies, and those patients actually can benefit from increased fetal surveillance. The pregnancies, again, if you do a mosaicism calculation, you show that the placenta is predominantly trisomic, then our data would suggest, and we've got a lot more data now and a lot with trisomy 16, it's almost inevitable that the pregnancy will be growth restricted, that it will be at risk for preterm birth, that the risk of true fetal mosaicism will be higher. Yes, I agree that they are awkward counselling issues. Even at the genetics end testing, they're awkward issues. but at least that patient who has been consented to have that test now has that information, and her and her partner can make decisions on the basis of the test results that come through and the counselling that they receive.
I'd be interested in Francesca's response to
I would like to know. I would like to have a reply for you, but what we want is largely dependent on the type of test counseling which is provided about this kind of tests and the results that are the incidental findings that can be detected, and on the fact that these incidental findings, even after an invasive procedure, cannot be solved. Okay. The problem, yes, of course, there is a benefit of finding translocations or recurrent partial imbalances, but this happens at the cost of finding a lot of more rare autosomal trisomies that in proportions are a bigger issue. And also for structural imbalances, there are some translocations that are not recurrent, and therefore they are as complex as rare autosomal trisomies to be interpreted. Finally, there is no study that demonstrates that a more strict monitoring of the CPM cases, clinical monitoring with ultrasound scan, serial ultrasound scan, may improve the clinical outcome of these CPM cases. So the problem is still extremely debated, and I think that in this moment there are more uncertainty than certainties with the so-called incidental findings.
I think we have one more question coming up.
Yes. Well, more than a question is maybe a comment or a question to the whole audience. I work in the Netherlands, and I'm also part of the Trident study. The Trident study will hopefully say what is the opinion of women. I hope that this will be reported sincerely, because I really question the fact that, as you said, 80% of Dutch women choose for this test. If you go to see your midwife and she tells you, you take part to a study, you have to pay 175 euros. Do you want to be tested for 3 trisomy or for everything? I bet anything you want that the majority will say that they want to be tested for everything. That they are not well informed because this is a too difficult and complex material for the majority of people to understand is proven by the fact that I see them when they have a positive test and they are really regretting deeply what they did. They didn't have a clue of what they were going to face. And the uncertainty, and even in case of a true mosaicist trisomy 16 that delivered last week a baby of 3,200 grams, I can tell you that that woman went through a hell, and she was really counseled to terminate the pregnancy in view of the findings. And I really think that this hasn't got anything to do with the criteria of Jungner and Nelson and Wilson and Jungner about screening, anything to do, and anything to do with screening for pregnancy complication. In our advanced world, we don't screen for IUGR, which affects 10% of our population, and we should screen for these rare trisomies. This is my comment and my sincere opinion.
Okay, I'm sorry, we're kind of looking to keep right on time. So we're going to have some rebuttals, and then we're going to have a little bit of time thereafter, just before we wrap up. So, Mark, this is a strict 5 minutes, okay?
All right, I have to quickly go through all the things that were raised. Last point was very good, and yes, it gets back to informed consent. So patients who are having these tests have to understand what they're saying yes to. My generic counsellors say there is no such thing as informed consent, so whether we don't test anyone or we realise there's some insufficiency there. Francesca's data set, the fetal growth restriction data set of 443 patients, I think in the end, after excluding people and others that couldn't be followed up, I think there was only 181 that were included, which means that she'd lost 70% of that data set. Of the ones that were included, I know that 40% of them were CPM type 2s, and I've said that those pregnancies are rarely, if ever, problematic with fetal growth restrictions, so they probably should have been removed from the data set. I just want to make the point that it's not an issue of reporting every rat that comes along. In my own laboratory, we detect rare trisomy, we apply bioinformatics, and we make a decision sometimes not to report those results. It's not a question of just throwing data into a sequencer and saying, oh, it reached this level, out it goes. So I would say we need to be more sophisticated about what we're doing. There's a saying in Australia, don't throw the baby out with the bathwater. I don't know if it's a worldwide saying. But we need to be sensible and specific about what we're doing. So I'll just say that. Francesca said that we shouldn't use CVS data to draw conclusions about the cfDNA screening and vice versa, but I think that's exactly what she's doing here. She's taking CVS data and making assumptions about what occurs at cfDNA screening. And again, I'll make the point that if you do this screening appropriately, it does have good clinical benefit, and that will extend into segmental aneuploidies, etc. I made the point that we had 3 out of 6 UPD cases that were confirmed pathogenic UPD, 6 cases from 54,000 pregnancies. 6 women were told that they were at increased risk for a pathogenic UPD. Okay, it's only 1 in 10,000, but if you're that patient, that may be important to you. Okay, so let's think more about personalised medicine and not throwing 100 women into a bucket together and saying you were the unlucky one, but it doesn't matter, you don't have to know. Again, I know that patients do appreciate being told why they have miscarried rather than getting no result or a normal result. I would say to Francesca, you said that 40% of miscarriage was inconsequential. I would say that to a patient who has miscarried, whether her pregnancy is inconsequential. I think they would argue against that. Again, we live in an era of personalised genomic medicine. I think we need to apply data to the specific cases at hand. The study of David Amor, which I'm a co-author on. Dave is in the audience. Where are you, Dave? You need to get up and defend that. The reason why that study shows no association with a poor outcome is very simple. In 1987, we stopped doing short-term cultures because we found that they were unreliable. And we just use long-term cultures, and we've done it for 30 years, and I think we do it very, very successfully. So all the cases in that study are actually mainly CPM2 cases. So there's sorts of cases that don't show any sort of any consequential outcome. So actually the data is exactly the way that it should be. So it did show what it should be. It also included things like sex chromosome mosaics, marker mosaics. So again, you need to look at the data. You need to look at what's in the data set and does it make sense. So I'll just say that about that one. One more, 1 minute. Oh, thank you. ACMG guidelines, yes, no professional society recommends expanded screening at the moment. Most of the guidelines were published, I know the ACMG ones in 2015, 2016. They are starting to become out of date, and the technology is moving along very, very quickly. There is a little comment at the very start of the ACMG guidelines, and it says that, I was supposed to write it down because I thought it might come up, but it basically advised clinicians that they should take into account new data as it becomes available. Okay, so we're 4 years down the track now. There is new data available, but what we need to make sure is that we've got the research around that data so that when we make recommendations, they're the right recommendations for the community. Informed consent is important, and I'll leave it there because I've got 22 seconds. I'm going to end early. I'm going to say that if you do it properly, the benefits of screening for rare autosomal trisomies outweigh the harms.
So first of all, I want to clarify that the CPM2 are not detected by cell-free DNA neither. the cytotrophoblast is normal, and we have performed a secondary analysis of our study on clinical outcome of CPM that will be published very soon, that shows that CPM2 are not associated with adverse clinical outcomes, in particular fetal growth restriction, while CPM3 are. I have a nice story for you. Yes, there is a story. So I start to summarize. The problem is that with cell-free test, rat-positive results with cell-free test, there are a lot of uncertainty that should be commented during the post-test counseling. The most important sources for uncertainty are the miscarriage and true fetal mosaicism. For miscarriage, about a large portion of the rat-positive results are due to miscarriage, and these are conditions that are very, and the counseling is extremely challenging with these cases due to the non-preventability and non-actionability of such condition, and the SCMG does not recommend to perform a screening for lethal conditions. Also, the TFM is another problem with rat-positive results, because a TFM does not necessarily mean that the fetus will be abnormal or even mildly abnormal, It could be completely normal, and CBS data cannot be used to directly used to counsel cell-free DNA in women. Because these two types of assortment are completely different. Rats in cell-free DNA include this miscarriage. Cell-free DNA reflects the whole apoptotic placenta, while CBS is a local biopsy analyzing viable growing cells, because these are cell-free DNA tests are based on variable methods and variable cutoffs. Cell-free DNA test is often subsequent to a serum screening or an abnormal ultrasound, and there are variable management protocols both in rat-positive results in cell-free DNA and in CBS. And therefore, CBS and cell-free DNA tests are likely to identify two different groups of pregnancies. Again, I want to reiterate that MPSS is a cell-free DNA test for rats is an opportunistic approach driven by the availability of a technical and powerful technology, the MPSS. And this reminds me the story of the pedoscope. The pedoscope, or shoe-fitting fluoroscope, is a very little known application of the X-ray, which is for sure a great new technology. The pedoscope is a machine that was installed between 20s and 70s in different countries and in shoe shops. And this is a metal construction covered in wood, in which which there is a porthole here, where an opening here, where the babies, the children, put their feet in the shoes inside, and while remaining in a standing position, they watch the X-ray image of their feet in the shoes, while watching here from the viewing porthole at the top of the machine. So in those years, children were regularly exposed to harmful radiations. This machine was sold as a scientific way to approaching the problem of poorly fitted shoes, eliminating the guessworks. Obviously, after dropping the atomic bombs in Japan, the researchers knew more about the shoe fitting fluoroscope and know more about the harmful radiation exposure. However, and obviously health departments and medical journals were very concerned about this machine. However, a nationwide ban of this machine never occurred. So my concern is if the genome-wide cell-free test for rats is becoming the pedoscope of the 21st century. So I have provided you many arguments showing that the overall benefits of screening for rats do not outweigh the harms, and that screening for rats in cell-free DNA is not so innocuous as opening the kimono, but is as harmful as opening the Pandora's box. And thank you very much.
So I definitely want to thank Francesca and Mark for both individually providing very compelling stories and evidence and arguments. I would say to you that, oh wow, look at that. As we're looking at the poll, which is jumping up and down, certainly one thing which is apparent to me is that they both agree that these are different data sets. And I think that really compels us to do further studies looking at extended NRPT. Mark has shown, I think, from his data set, adverse outcomes, but it would be great for us to continue that work and really show that, universally worldwide. I think what's become apparent is we need to know how to deal with these things. So, and that kind of supports what Francesca said. We want to do good on our patients, and certainly understanding that there could be potential problems is a benefit we can help them with, but unless we know how to counsel them, we can do added harms as well. So I think we need to be investigating the appropriate management of these, of our patients when we find these rare autosomal trisomies. And, a good point was made, do our patients really want to actually know this type of information? And so certainly while 80% of them may want them from the Trident study, I think a good point was raised that do they really know what they are getting? And so focusing on our patients who have gone through this experience with post, kind of pre and post test questionnaires and interviews, I think is going to be very beneficial to understand exactly how we can help them and how we can improve it. Wow. Tell them that I like it. Okay, wait, we're waiting for just 2 more percent. Well, it's fantastic. I really think both of them have done an outstanding job. I really do want to thank both of them. I want to thank our supporters. And I think we've really set the stage for a terrific meeting. So we'll see you all at the exhibits. And I think we are heading for the opening session. So have a good evening, everyone. Thanks.
Okay, so there will be there's drinks and cannabis at the welcome reception next door. So those of you who are going for the dine around, please meet your groups at the registration counter at 7:15. And tomorrow morning at the 6th, breakfast will be served.
You all want to record? Huh?